Okay, so today we are talking about the relationship between Gibbs free energy and the equilibrium constant. K comes back into your life again with all the joys that the equilibrium constant will bring. And so we're going to talk about the relationship between equilibrium constant and Gibbs free energy. You're going to need your reference page in order to do these problems. So if you've lost it, there's one posted on the course website. It's also in the appendix in the back of your textbook, and there are about a zillion of them just freely floating around the internet as well. Okay, so you're going to need your reference page for these kinds of problems. So I want to show you an example. This is actually from an organic chem textbook, because I know a lot of people in Gen Chem are like, just let me do my calculations and let me leave, and I'll never think about this stuff again, right? Well, if you're going on to take organic, you're going to see it again. This is from an organic chem textbook. This is actually the book that we use here on our campus. So we're going to talk about kinetic versus thermodynamic control. So if I have this reactant and this reactant, and you don't need to worry about the names in this class, it's going to produce an intermediate, and then the final product is going to be determined by how the reaction is controlled. Is it controlled by kinetics, or is it being controlled by thermodynamics? So depending on the temperature, negative 80 degrees Celsius, you'll be under what's called kinetic control. You'll get primarily this product in green. The bromine goes here in the kinetic product, and that's the primary product. Versus at 40 degrees Celsius, the bromine goes here. That's under thermodynamic control. So this is called the 1,2 product. Again, you don't need to know how to name that because you're not organic students yet. This is called the 1,4 product. Again, you don't need to know how to name this because you're not organic students. But the temperature determines the primary product at kinetic control versus thermodynamic control. So what do I mean by that? Here's the 1,2 product. If we're at a temperature of negative 80, the 1,2 has a lower activation energy, right? That's a lower barrier to overcome at that temperature. So it's going to occur really fast. Because kinetics is determining the product at this temperature, that's why we say it's kinetic control. Now, at 40 degrees Celsius, that's an entirely different temperature. Remember, I told you all this stuff's temperature dependent, right? Equilibrium constant is temperature dependent. Gibbs free energy is temperature dependent. When we're at 40 degrees Celsius, we get into an equilibrium situation. And equilibrium prefers the more stable product. This product's more stable because that's the more substituted double bond. Again, that's not something you need to know for Gen Chem. But because thermodynamics is determining which product is the major product, that's why we say we're under thermodynamic control. So this is something that you will see in organic chem. I promise you, right? The equilibrium constant, Gibbs free energy, all that wonderful stuff that you're just kind of like grinding through now, it's going to come back to the picture. It's going to have real-world consequences when you get to organic chem and beyond. When you're at negative 80, you have kinetic control. The product that's formed faster is what predominates. When you're at temperature 40, and again, it's because it's got the lower activation energy. When you're at the temperature of 40, right, that gets you into an equilibrium situation, which is going to prefer the more stable product, right? And that is why this is called the thermodynamic product versus the kinetic product. And again, this is all temperature dependent. It's all temperature dependent. So I hope that you at least take from this the idea that we can't conclude something at one temp is going to work for every temp. And also I hope you take from this the idea that please keep at least a little nugget of this information stored in the back of your brain for your future classes, because you're going to see it again. All right, let's move back to today's stuff. What is the thermodynamic definition of equilibrium? It's when delta G equals 0. In terms of thermodynamics, equilibrium occurs when delta G is 0. Delta G is 0. And these notes are already posted on the course website, so if you missed something, you can go back and grab it from there. Delta G equals 0, that means you're at equilibrium. All right, so let's talk about the relationship between thermo and equilibrium. Both of these things, both delta G and K, are both looking at the same thing. They're basically looking at, are you reactant favored or are you product favored, right? Because if K is greater than 1, we can determine that it's product favored. And if K is less than 1, we can determine that it's reactant favored, right? If delta G is negative, we can conclude that it's product favored. If delta G is positive, we can conclude that it's reactive favored. And so the larger the value of K is, this is a quantitative relationship. You can do some math and prove this to yourself. The larger the value of K, the more negative the value of delta G is. And the negative delta G means that the forward reaction is spontaneous, right? This is what we learned last week. If you do the calculations and you get a negative delta G, let's just say you get delta G equals negative 5 times 10 to the 50th, right? Big negative delta G, that means that the forward reaction is spontaneous. In other words, it's product favored, right? And then if we have delta G equals 0, that means we're at equilibrium. So we're not product favored, we're not reactant favored, we're at equilibrium. This and this are occurring at the same rate. And then if you get a big positive delta G, right, so you get delta G equals 5,000 as opposed to negative 5,000, right, you get the reverse reaction is occurring spontaneously. In other words, we are reactant favored. So do you see how delta G and K are telling us the same information? Right, this is literally all the same stuff we said last week. The only part that's new is that thermodynamic definition of equilibrium when delta G equals 0. So here's some pictures. If we've got N2 plus 3H2 equilibrium with 2NH3, this is the Haber process, Nobel Prize winning reaction here, right? If we have pure reactants, that would mean that we have a positive delta G, and that would mean that K is less than 1. If we have an equilibrium mixture, that would mean that K equals 1, delta G equals 0. Right? We knew this from our equilibrium studies. And we knew this from our equilibrium studies. We knew this from last week. And if you have negative delta G and K greater than 1, right, you've got pure product. Is everyone with me so far conceptually in terms of the concepts? I left anyone behind? All right. Because a lot of this is review. Really, this is the only new part so far. And again, there are data that you can use to just show this, right? If delta G is 0 and K is 1, there's equilibrium, right? And now here's product favored. Here's reactant favored, and here's product favored. So the mathematical relationship that I keep alluding to is this one. Delta G of the reaction is equal to negative RT times the natural log of K. Now last week we didn't deal with any logs. All we did was adding and subtracting and multiplying. This week, natural log comes back into the picture. Everybody's favorite, right? Taking natural logs. What's R? R is 8.314 joules per Kelvin mole. That value will be given to you on your reference page. Okay, you'll probably memorize it just from using it so much. T is the Kelvin temperature. And what's K? Please tell me you know this one. K is the rate constant or the equilibrium constant? Which one is it? Equilibrium, right? We haven't mentioned the rate constant in a long time. So H 3.14 joules per Kelvin mole. There is a negative built into the equation. So if you want to put parentheses around that, I guess you could. There's a negative built into this. T is the Kelvin temperature. How do we convert Celsius to Kelvin? At 273, right? And then K is the equilibrium constant. We learned how to calculate delta G last week. How do you calculate delta G? Delta H minus T delta S, right? We learned how to do that last week. All right, so let's do this one together. Calculate K at 25 degrees Celsius for this reaction. Now this is the formation of rust. Does rust form spontaneously? If you have an exposed metal on your car, yes, rust will form spontaneously, right? That's why everybody's like obsessed with washing their cars, especially after winter. So I want to know, at 25 degrees Celsius, what is the equilibrium constant? And is it reactant favored or product favored? Or maybe at that temperature I'm at equilibrium, who knows? So we first got to write a balanced chemical equation. And then step 2, we got to get out our wonderful reference page, right? Because we can't do any of this without our reference information, because you're not going to be expected to memorize thermodynamic constants. That's just insane. And then we're just taking what we did last week a step further. So first thing we have to do is you have to calculate delta G. Okay? What's the formula for delta G? Delta H minus T delta S, right? So I've got to calculate delta H. How do I do that? We did this last week. Products minus reactants or reactants minus products? It's products minus reactants, right? Delta is always final minus initial. So it's the sum of the products minus the sum of the reactants. All right, so the heat of formation of rust is negative 826 multiplied by 2. From that, I subtract 0 and 0. These are both 0 because they're pure elements in their most stable form. And if you don't believe me, just look at your reference page. Gives me an answer in kilojoules. I'm going to convert everything to joules. Anyone want to take a guess why I'm keeping everything in joules? The answer is not just for fun. Go back and look at my equation. What's R in? Joules, right? So I'm going to keep everything in joules, or you could convert R to kilojoules. Whichever makes you happy. I don't care. But make sure your units make sense, okay? Because if you've got your delta G calculation in kilojoules and you try to plug that in with an R that's in joules, there's going to be a clash. Right? It's not going to work. So to calculate delta H, sum of the products minus sum of the reactants, what we did last week. Now we got to calculate delta S. Again, sum of the products, so coefficient of 2, delta S for rust, minus coefficient of 3, there's delta S for O2 gas, plus 4 times the delta S of iron metal. Again, this comes out in joules automatically. Right? Delta S comes out in joules by default. Delta H comes out in kilojoules by default. So I converted my delta H to joules. This one's already in joules. So this is exactly the procedure we learned last week. Like, this is literally not new. Right? We learned how to do this last week. We even did enrichment. So there's delta G. I get negative 1.49 times 10 to the 6 joules. Based solely on delta G, I can conclude if this is spontaneous at that temp. Is it? Yes, right? That's a large negative value of delta G. So yes, I can conclude that this is spontaneous, but the problem asked for the equilibrium constant, right? So to get equilibrium constant, work with me here, clicker. I plug into this equation. That's the new equation for today, right? I take my value that I just obtained. R is negative 8.314. I lost a digit there. Temperature is 25 degrees Celsius, which is 298 Kelvin. So now I'm just solving for natural log of K. Right? So this times this gives me this. Yes. How do I get natural log of K by itself? Divide both sides by negative 2.48 times 10 to the third. Right? So I get 601 is equal to natural log of K. Now, how do you get rid of a natural log? A natural log is a logarithm with base what? E, right? Euler's number. So if this were log, you'd raise both sides to the 10 to get rid of a log. How do you get rid of a natural log? Raise both sides to the E, right, to Euler's number. So K is equal to e to the 601. Now, if your calculator says error when you enter that, and many calculators do, depends on your calculator, 601 e to the x. Yeah, mine says error. Mine can't compute that, because I definitely remember having to go to a more powerful machine. If your calculator says error, e to the 601 is an acceptable answer. You can put that as your answer. Okay, that's just like saying 3 pi over 2. Right? That's an acceptable answer. So if your calculator cannot turn that into a decimal, don't worry. Just say e to the 601. Is that going to be a number greater than 1? Yes, it's going to be a number significantly greater than 1. Right? So is this value corresponding to the value that we got for delta G? large negative delta G corresponding to a large positive K. So these two go hand in hand, they're opposite each other, right? If delta G is a large negative number, you should expect K to be a large positive number. Now, is it always going to be that big? No, but in this case, it works out to be that big. Does everyone see how we do this? So step one, you already know, right? You learned how to do delta G calculations last week. The only new part this week is learning how to calculate K. So we take that information we learned how to do last week, we're taking it a step further. Questions on how to do this? Okay. Come on. Why aren't you working? All right, so here's one for you to try. What is K at 50 degrees Celsius for this reaction? And I want to know, is it reactant favored, product favored, and is it spontaneous or non-spontaneous? So I'm going to pause it and let you try. Zoom. All right, let's go through this and see what you got. So before we can do anything, what do we have to calculate first? Can we calculate K just straight out of the gate? Definitely not, right? We're not making an ice table. We're not given any information that we could use to make an ice table, even if we wanted to, right? All we know is a temperature. So we have to calculate what before we can calculate K? Delta G, right? So we calculate delta G, delta H minus T delta S, which means, got to calculate delta H, right? 2 times the heat of formation for NO2 minus heat of formation for N2O4. This gives me an answer in kilojoules, which I then am converting to joules, because ultimately my K equation is going to need me to be in joules. Delta S, 2 times the delta S for NO2 minus delta S for N2O4, right? It's products minus reactants. This gives me an answer in joules already, so I don't need to do any conversions there. Now I can plug into delta G, delta H minus T delta S. So my value from here minus this is my Kelvin temperature, right? 176. Notice joules in joules per Kelvin, right? This is in Kelvin, this is in joules per Kelvin. Kelvins cancel, so it ends up being joules minus joules. So that's how I get an answer in joules here. Based on this delta G, could we make a conclusion? We could, right? We're not going to based just on that, but we could. What would we say if we just had delta G? Spontaneous or non-spontaneous at this temp? Non-spontaneous, right. But let's take it a step further, because that's what the problem asked me to do. We want to know what K is. We want to know what the equilibrium constant is. So I'm just plugging my value that I just obtained into the delta G equation. There's my Kelvin temperature again. R is a constant, solving for natural log of K. All right, so this times this gives me this. Divide both sides by negative 2,685. And that gives me negative 0.1311, right? Because that's a negative, that's a positive. So that means that K is Euler's number raised to the negative 0.1311. So that's 0.877. Based on a K of 0.877, would you conclude that it's reactant favored or product favored? Is that greater than 1 or less than 1? That's less than 1. So what do we say? Reactant or product favored? Reactant. Does this answer make sense in light of this answer? Yes, delta G is positive. Therefore, K should be less than 1. And it is. Right? These two are going to go hand in hand. You're going to have a reactant favored conclusion based on delta G. You should also get a reactant favored conclusion based on K. They should go hand in hand, and if they don't, that's a red flag to go back and double check your math. Okay? Because if you're calculating K and you somehow got this to be product favored, but the delta G is positive, something's wrong with your arithmetic. Okay? So at this temperature, we would say no, it's not reactant, it's reactant favored, it's not spontaneous. So the next thing we need to look at is just for fun, right? If you want to take this equation and rearrange it To save yourself the algebra, you can, because all we're doing is just rearranging. Divide both sides by RT and take E. This is the same thing as this. So if you see it in a textbook written this way, know that it's the same thing as this. Okay, that's not, it's just a rearrangement of this. So if you ever see that, don't let it throw you off. So in that previous problem, we came out non-spontaneous reactant favored, right? That temperature was not good enough to get us to spontaneous. So my question now becomes, at what temperature will it become spontaneous, right? Because at some temperature, that is going to become spontaneous. Just because it's non-spontaneous at one temp doesn't mean it's always going to be non-spontaneous, right? So we need to calculate the minimum temperature in order to get a spontaneous reaction. And so what we're going to do here is we're just going to look at our definitions. If delta G is 0, right, that means you're at equilibrium. Yes? That's thermodynamic definition of equilibrium. And if delta G is greater than 0, you're spontaneous. That should be delta G is less than 0. Not greater than. Delta G is less than 0. Delta G is negative. Right? So if we substitute in 0 as delta G here and solve for T, that gives us a minimum temperature that we need to be at to achieve spontaneity. Okay? So any temperature, when we substitute 0 in, that's the minimum temp we need to be at to get to spontaneity. So let's do this one together. Let's just pretend you've already done the delta H and the delta S, save you the work. You came up with delta H and delta S already, and I want to know at what Celsius temperature will this reaction become spontaneous. So make sure my units match here, right? I don't care which way you convert it because we're not dealing with the K equation. So whichever way you want to convert it to make you happy, I just converted joules to kilojoules. Oh, I don't know why the answer showed up first, right? Plugging in 0 equals delta H minus T delta S. So plugging in delta H, plugging in delta S, solving for T, right? So T is equal to this over this. So that's 419 Kelvin, which I said in the problem I wanted to know the Celsius temperature. That would be 146 degrees Celsius. Pretty sure there's one like this on your upcoming homework. Does everyone understand how to do it? You're just plugging in 0 as delta G and solving for T. Now, if I didn't give you delta H and delta S, you'd obviously have to calculate those first and plug those in. But since I gave you delta H and delta S in advance, that makes it a little easier. All right, so here's a practice problem for you to try. Theoretically, again, theoretically, solid calcium hydroxide can decompose into water vapor and solid calcium oxide, in theory. Will this reaction occur spontaneously at a temperature of 33 degrees Celsius? You take a second and try this one. All right, let's go through it. So, we have to write a balanced equation before we can do anything. I asked calcium hydroxide is being decomposed into calcium oxide and water vapor. First thing you have to do is you got to calculate delta G, right? There's delta G. But before we can do delta G, you got to calculate delta H, right? So products coming from here and minus reactants. So that gives me delta H. Products minus reactants. So that gives me this. And here's my delta G. I kept it in kilojoules because the problem doesn't ask me to calculate equilibrium constant, right? If you're not required to calculate the equilibrium constant, then who cares what your units of G are, right? Based on this delta G of 65.2, that's greater than 0. Greater than 0, so no, it's not going to occur spontaneously, right? I mean, and you guys have worked with solid calcium hydroxide before. You've dealt with it. You've worked with it in the lab, right? It didn't spontaneously decompose In fact, it does the opposite. It absorbs H2O. It doesn't spontaneously decompose. It actually absorbs it. So no, this is not a spontaneous reaction at 33 degrees Celsius. So then, if it's not spontaneous at 33 degrees Celsius, at what temperature would you have to be in order for it to become spontaneous? Take a second and try this one. So how would we figure out this one? We would plug in 0 for what? In this equation, which value would we turn into 0? Delta G, all right? We're going to solve for T, because we solved for delta H and delta S already in part 1. We've already done that. So, woohoo, don't need to do that over again. We've already done it. So now I'm just plugging in delta H minus T delta S equals 0. So now I just plug them in, do some math. 760 Kelvin, which would be 487 degrees Celsius. So if you want this reaction to occur spontaneously, are you going to have to heat your sample or cool your sample? You're going to have to heat it in a furnace, right? 487 degrees Celsius is hot. That's really hot. Right? That's not something that's going to be spontaneous at room temperature. It's not going to be spontaneous for a long time until you hit 487. Do we see how we did this one? All right, here's another one for you to try. You've got C6H6 in equilibrium with C2H2. That's benzene and acetylene. Both liquids. What's the equilibrium constant at 40 degrees Celsius? And is it reactant or product favored? So take a second and think about this one. Okay, so these are both liquids. That does make a difference when you're looking at your reference page. Make sure that you're looking at C6H6 liquid versus C6H6 gas. Okay, they are different values. Remember that these thermodynamic values are phase dependent. C2H2 liquid is also going to be different than C2H2 gas. So make sure you're looking at your phase when you're doing these kinds of problems. So first we're going to calculate delta G, right? Which means we have to calculate delta S and delta H first. So based on this, I get a delta G of 4.92 times 10 to the 5th, right? That's really, 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 really reactive favored because that's a large positive number. So my K, should my K be a large number, greater than 1, or a large exponent or a small exponent? 10 to the negative 80th versus 10 to the 80th. Which one should it be? If this is G, should K be large and positive, or should K be a small number, less than 1? It should be less than 1. Let's see if we get a K that corresponds to that. We do. Right? When you do the arithmetic, I got e to the negative 183. Right? That's, when you put it into your calculator, 3.34 times 10 to the negative 80th. That's really, really reactant favored. There's the calculation of where we got it. All right, we just plugged in delta G, negative RT, ln K. All right. Plug, rearrange, rearrange, rearrange. If delta G is a large positive number, K should be a large negative number. And they are in agreement here. Large positive, small number less than 1, those two make us come to the same conclusion. So you would have all benzene and no acetylene. Do we agree? All right, last one. You're studying this reaction at 310 Kelvin, and I've given you delta H and I've given you delta S. You've already determined that. You were working in the lab and you determined this in advance. And I just want to know, is this a spontaneous reaction at this temperature? Yes or no? So I'll pause it and let's try this one. All right, so since we already know delta H, we already know delta S, all we have to do is plug into delta G, because the problem doesn't say what's the equilibrium constant. The problem just says, is it spontaneous? All right, so I don't even need to calculate K because the problem didn't ask what's the equilibrium constant. It just says is it spontaneous. And to conclude that, I really only need to calculate delta G. Delta G is negative 147. So I would say, yes, it's spontaneous, which would also mean that it's product favored. Does everyone see why we didn't have to calculate K here? Problem didn't ask for it. It just said, is it spontaneous? Delta G is enough to conclude if something's spontaneous or not. Now, if I said, what's the equilibrium constant, then obviously we'd have to go another step. So Wednesday, we're going to be doing enrichment on this stuff. Make sure you bring your reference information with you, or your phone. Like I need to tell you to do that, right? Make sure you have some way of accessing the reference information because on Wednesday, we're doing enrichment on this stuff, and I'll see you then.